This part of the story is called Newtonian dynamics. We're going to try to think about what causes motion. We've just talked about kinematics, the description of motion. Now we want to think about what causes motion, specifically what causes a change in the state of motion. State of motion, velocity, change in the state of motion, change in velocity, the rate of that change, how fast is that change happening, acceleration. In other words, we're trying to think about what causes acceleration. Or really, what are the factors that determine the acceleration of an object? For example, why did we say that in free fall, the acceleration of the object is exactly 9.8 and so on, meters per second squared? So we want to know what is it in the object itself and what is it in the circumstance of the object that determines the change in the state of motion of the object. So you say, in the object itself, what I notice is that certain objects, when I try to change their state of motion, resist that change more than other objects. See, what physical quantity, what property of the object makes it resist less or more? Turns out that property is called mass. We give it the name mass. Now, a lot of definitions of mass, and you'll see in some textbooks that the definition of mass is that it's basically quantification of how much matter there is. And I suppose in a sense, maybe that is technically, okay, a fine definition, but for me, it kind of has a circularity to it that is unsatisfactory because you say, well, okay, so it's about the quantity of matter. Like the mass of an object is about the mass of the constituents or something like that, right? And then you say, what about the mass of the constituents? How do you define that and so on? So I feel like a better definition, especially a better working definition, because if you remember, mass is one of the base quantities, one of the fundamental quantities. So it's basically defined by the way it's measured rather than in relation to other things. How do you measure it? Well, basically, you try to accelerate an object and you see how much it resists it. And that's exactly how you figure it out. So mass is really a quantification or a measure of the object's tendency to resist any kind of change in its state of motion. State of motion means velocity. The rate of change in the state of motion is called acceleration. The tendency of an object to resist that is a concept that we call inertia. So really, mass is a quantification of inertia, a measure of the inertia of an object. So that's in the object itself. And then the second piece, then you ask, well, what about the external stuff? You know, because I can have the same object accelerating at two different rates. So what actually decides what rate this object is going to accelerate at? Turns out that's something that we call the net external force. So three things we want to think about. What does net mean? What does external mean? What does force mean? Start with the last one. In physics, force is a way that we think about defining the interaction between objects. So one way you can think about it is you can say there is an interaction between the objects. How can I represent the influence of one object on the other one? We call that a force. External means that part, that it's a force that comes from outside the system into the system, or like it's acting on the system. If I think of myself as a whole system and I say, oh, this is an internal force, part of the system is acting on another part of the system. But whatever object is external acting, we call that an external force. What does net mean? Well, to understand what net means, first you have to understand that a force is a vector quantity, is mathematically represented by a vector. So we call it a vector quantity in short. Vector means, magnitude and direction are important. Without mentioning the magnitude and the direction of the force, you have not completely described the force. So a force in this direction is not the same as a force in this direction. Push is not a pull. So that means then that if I have two people trying to push a car, for example, if they're pushing in the same direction, that's different than if they're pushing in the opposite directions of each other. So the concept of the net force means the overall sum of these forces, thinking of each force as a vector. So this is a vector sum. Think about the tool that is a coordinate system in which you can describe these vectors, and then you perform the addition operation depending on the mathematics of that particular coordinate system. So in Cartesian coordinates, for example, you say x, y, and z in three-dimensional space. You put a force vector here, so it'll have an I hat, a j hat, and a k hat component, and another force in another direction, another force in another direction. The way you add forces is you add the I hats together, you add the j hats together, the x. So I can start by thinking about resolving every force into its components, and then add each component separately, and then you find the net force in terms of its components. You can leave it in that form, but if you also want its magnitude and its direction, you can use your vector mathematics to find the magnitude and the direction of that vector. So that's your net external force. The idea of the net external force is so important. And we have 3 laws to describe the dynamics, its interaction with the internal resistance of the system, and how that produces the acceleration. Okay, the first one says the following. It says, if the net external force on a system is 0, the system will not accelerate. We call that equilibrium condition. And it's implied either way. It's if and only if. In other words, if the system is not accelerating, I can deduce that the net external force on it is 0. If the system is accelerating, then I can deduce that the net force on it is not 0, and vice versa. Is that if the net force is 0, no acceleration. If the net force is not 0, acceleration. Now, no acceleration equals 0. We know that. That means you're either moving with constant velocity, so your velocity vector is not changing. And of course, velocity vector not changing means both magnitude and direction. So for example, circular motion, we know that there's acceleration in circular motion. So that means there must be a net force in that case because the velocity vector is changing. Maybe it's not changing its magnitude, but it's changing the direction. And that's a change. And that change means acceleration. And that acceleration implies that there's a net force acting on that object. So the first law, which sometimes is also called the law of inertia, which sometimes is also attributed to Galileo. Any object in a state of motion tends to maintain that state of motion unless compelled by an external force. In other words, if the object is at rest, it will stay at rest, again, relative to whatever coordinate system, because remember, position is relative. So if a system is at rest in some coordinate system, in some inertial reference system, it will stay at rest in that system. If it's moving with constant velocity, then it will stay moving with constant velocity unless it is compelled by an external net force. So that means that in principle, if I throw an object, it should just continue at that rate, at that state of motion, unless there is some external force acting on it. So the fact that I throw an object and it doesn't continue like that means that there is some force acting on it. That's the deduction. Okay. The second rule says, what happens then if the net force is not 0? The net external force is not 0. What do I do? Because if it is 0, then there is no acceleration. But if it's not 0, there must be acceleration then. Now that question is, well, how big is that acceleration? See, listen, it is reasonable. First of all, this is a law that what I'm going to tell you about in a second. So that law, we know it's a pattern that we observe in nature, it works and so on. But I'm gonna give you some intuition about where, why it would, why it's, it is reasonable. So first you say, if I have the same object and the net external force on it doubles. So one person was pushing the car, now 2 people are, and let's say no other forces are acting on it. So if the net external force doubles acting on it, the expectation is that the acceleration is also going to double. On the other hand, when you think about the resistance to the acceleration, which we call the mass of the object, you can imagine a more massive object. If you act with the same net external force on a more massive object and less massive object, you would expect the more massive object to have less acceleration because it resists the acceleration more. And that's it. That's the rule. The rule is that the acceleration is proportional to the net force and inversely proportional to the mass. So A is equal to sigma F over m. And you say, this is also a vector equation because the acceleration is a vector and the net force is a vector. So basically, the acceleration is just the scaling of that net force vector. Scaled by what? By the resistance, by the mass. The bigger the mass, the smaller the acceleration becomes. So the more that net force, anyways, you understand what I'm talking about with the vector, scaling the vector by the scalar, which is 1 over the mass. But the other thing that you realize too is that I remember that when a vector is multiplied by a scalar, that vector, all that happens to it is that its components also get scaled by the same thing, and its magnitude gets scaled by the same thing, but its direction stays the same. So in other words, what we're saying here is that the acceleration will be exactly in the same direction as the net force. Makes sense. If the net external force on an object is in this direction, I expect it to accelerate in this direction. I don't necessarily expect it to move in this direction, but I expect to accelerate in this direction. In other words, suppose something is coming this way, so that's its state of motion, and I apply a force perpendicular in this direction. I don't expect it to right away move like this. So it's not about the direction of the force is not going to be the direction of the motion. It's going to be the direction of the change in motion. So if something's coming this way, I apply a force in this direction, it's going to go like that. It's going to change the state of motion. So the rate of change of the state of motion, that's the acceleration. So the force is really causing acceleration, not causing motion. That's called Newton's second law, sometimes known as F equals ma. Third Newton law is about the fact that these forces, these things that we're talking about, are kind of fictitious things. The real thing is the interaction between the objects. But the force is kind of a description that we come up with to represent that interaction. So Newton's third law says that forces always come in pairs, because I'm representing the interaction of A and B. So it's the force of A on B and the force of B on A. I can't have a force of A on B without B acting on A, So that's the story, is that forces always come in pairs in nature like that. You don't find one force sort of sui generis out of nothing. They always come in pairs. And in fact, they always come in pairs that are opposite to each other and equal to each other. So the third rule is that the force of A on B is always equal to the force of B on A, but in the opposite direction. Sometimes it's known as the action-reaction laws, that if A acts on B, the other one has to react with the same, I don't know what this whole story is about, action-reaction stuff. Because action-reaction implies that one of them started it. But this is not how it happens in nature. It's not like someone started the interaction. The interaction happens between the two. The interaction is happening. And the description of the interaction in terms of forces can be written as two forces, the force of A on B and the force of B on A, but they're in opposite directions. And that's how we describe forces all the time. Now, the key point becomes, where do you put the boundary of the system that you want to study? Because inside the system, there are forces like that, in pairs and pairs and pairs and pairs and pairs. And that's why internal forces don't matter, because they're always coming in pairs. So they're always canceling each other until you come to the one where you put a boundary between the system you're studying and the system that you're going to call the rest of the universe, which is the environment, whatever else is acting on the system of interest. Then that's when you put that boundary, that's when you separate the forces. What's acting on my system and what's my system acting on the environment. Now, if I care about the system of interest, because by definition, that's the system of interest, something I care about, then if I care about my system of interest, then I will summarize the influence of the environment on my system, and I will not care about what my system does to the environment. And that's a concept that is known as the free body diagram. You say, let me think of my system. Let me ignore all of the internal forces in the system. And let me just think about that boundary where my system is interacting with other things. And I ask, how can I summarize that interaction in terms of forces that I can draw as vectors, as arrows, on my system to try to analyze the net external force that's acting on my system? And then you walk it backwards. So it's almost like you're starting with Newton's third law. So you say, when you first see a situation and you want to think about what's the acceleration of my object, or how can I, write these things, etc. How can I analyze the dynamics of the situation? You start from Newton's third law. You ask yourself, where's the boundary? What's my system? And how is my system interacting with the rest of the environment? And then I describe the influence of the environment on the system in terms of a free body diagram, in which I draw all of the actions on the system as forces, arrows, vectors, acting on the system. And then I think about these vectors, I add them in vector sense to find the net external force. And then it's either going to be one of two situations. I'm either going to be in equilibrium, net force equals 0 because there's no acceleration, or not in equilibrium, net force is equal to mass times acceleration, or acceleration equals to the net force divided by the mass. Either depending, so the situation could be, you're asking the question, is this object in equilibrium or not in equilibrium? Then you calculate the net force. Is it 0 or is it not 0? Or you could know that the object in equilibrium, and then therefore you start by writing, okay, what is the net force acting on this object? It must be 0, and then you set it equal to 0, and you find whatever it is that you're looking for. So these are typically the two kinds of situations that you're either wondering whether an object is in equilibrium or not, or you know that it's in equilibrium or not, and then you use that information to either set the net force equal to 0 or set the net force to be equal to mass times acceleration.